Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. Tonight we are going to pick up right where we left off and continue talking about our discussion on aqueous ionic equilibrium. Last week we had an excellent, great, very productive live stream. We did all the calculations associated with titrating a strong acid with a strong base, and what I liked so much about that stream was the level of engagement and participation that I got. It was awesome. There weren't a lot of people in the stream, as there are never a lot of people in this stream, but the people who were there were really engaged. They were following along. They had their scientific calculators. They were doing the calculations as we go along, making sure we all got the same thing. That is the kind of engagement and participation that I'm really going for and that I would love to have on all of my live streams, but of course, I will take it wherever I can get it. All right, guys, so without further ado, I'm going to go ahead and present to you. This is Aqueous Ionic Equilibrium, Volume 5. As always, your feedback is more than welcome and highly encouraged, so please, if you're watching this live, feel free to drop your thoughts in the chat, or, as I said previously, participate and follow along with us. And if you're watching this as a video, please leave me a comment. Without your feedback, I am completely lost. One more thing I want to announce is that this video and all of the Aqueous Ionic Equilibrium streams are compiled conveniently into a playlist called Aqueous Ionic Equilibrium live streams. You can find the link for that in the description below. All right, guys, so without further ado, let's go. So we're going to review the content from Volume 4 briefly. So in Volume 4, that was last week's stream, we introduced the concept of an acid-base titration, or just a titration generally. So generally speaking, you have a sample of something which we call the analyte, and you want to know what is the concentration of this stuff. I know the volume, that's easily measurable, but I want to know the concentration. Well, what you would do is you would perform a titration. That means carrying out a chemical reaction, a known chemical reaction with known stoichiometry. In other words, the balanced chemical equation of the reaction associated with that titration is known. You would react, and the material that you would drop into the analyte is called the titrant. Now, if we assume for the moment that the analyte is an acid, then your titrant would be a base, right? And if your analyte was a base, your titrant would be an acid for an acid-base titration, right? So your titrant has a known concentration, and what you do is you add it slowly to your analyte, you carry that reaction out, right? And eventually the reaction will be over, so you can figure out how much titrant you need to react with all of your analyte. That'll allow you to calculate your way to know how many moles of analyte there are. And if you have the number of moles and you have the volume, then you can calculate concentration. So that's basically what an acid-base titration is. There's another term that's valuable to us in the context of titrations. It's called equivalence point. That's the point where the amount of acid and base are equal. The moles of base is equal to the moles of acid. And how do you know when the reaction has reached its equivalence point? Well, you can use either a pH meter or an indicator, which is a substance whose color depends on the pH. All right. So what we did last week was we did a strong acid, strong base titration, right? So we had a problem in which we start out with a strong acid, HCl, and you add strong base to it, and you perform that titration, and you do all these calculations along the way. So we calculated the pH upon adding no titrant, no sodium hydroxide, followed by 10 mils, then 20 mils, then 40 mils, and so on and so forth. So that's what we did last week. So we're going to do something similar tonight. The only difference is, instead of doing a strong acid, strong base titration, we're going to do a weak acid, strong base titration. So we're going to do calculations associated with titrating a weak acid with a strong base. And we're going to see that the calculations are significantly more complicated because, again, for a weak acid, you don't have a full conversion from reactants to products. You have a partial conversion characterized by an equilibrium constant. So we have to invoke that into our calculations, right? So that's, again, what we're going to be doing is we're going to be titrating a weak acid with a strong base. Very excited about this. So we're going to do the same thing where we have the whiteboard open. We're going to do all of our calculations. We're going to have an Excel spreadsheet open where we can sort of input our pH values as we go along. And we're going to build a titration curve from beginning to end. So I need to grab my pen here. So here we go. All right, so here's the problem. So the problem is, where is it? There it is. So Okay, so here's the problem. So what we're going to be doing is we're going to be doing a titration curve for the titration of 100 milliliters of 1 molar nitrous acid, HNO2, which is a weak acid, of course. We're going to be titrating that with 1 molar sodium hydroxide. Now, for convenience sake, I've provided both the Ka and the pKa. Ka, again, that's the acid dissociation constant. It's basically the equilibrium that describes the strength of this weak acid here, 4.6 times 10 to the minus 4. And then to get the pKa of that, all you do is you take the negative logarithm of it, which I've done here. The pKa of nitrous acid is 3.34. Okay, so the first thing that we're going to calculate is the volume that's required to reach the equivalence point. Remember, the equivalence point, that's the point in the titration at which the number of moles of acid is equal to the number of moles of base. So bear with me while I write this real quick. Volume, I'll just say volume for equivalence, right? EQ, right? So we're trying to calculate the volume of sodium hydroxide that we need to add to this 100 ml sample of 1 molar nitrous acid to reach the equivalence point. So in order to do that, what we need to do is we need to take our 100 milliliters of nitrous acid and we need to convert that into moles of nitrous acid, because again, equivalence point is when the number of moles of acid in a base are equal, right? So if I start out with, say, my 100 milliliters of nitrous acid, HNO2, right? In order to use molarity, we're going to have to convert this volume in milliliters to liters, right? Because this capital M, that's molarity, right? Moles of solute per liter of solution. So we have to convert this to liters. Pretty easy conversion, right? Milliliters on the bottom, liters on top. There are 1,000 milliliters in 1 liter, right? And now that we have liters, we can use the molarity, in which it's going to be 1 mole per 1 liter, right? If you have a 1 molar solution, that means you have 1 mole of it per a liter of solution, right? Now, I'm doing 1 over 1. This step might seem mathematically unnecessary because, again, 1 divided by 1 is 1. But it's important to do this because the numbers won't always be so easy, and you want to make sure those units cancel out. So milliliters cancel with milliliters, liters, liters. So we have 100 divided by 1,000, which is equal to 0.1 moles of HNO2, 0.1 moles of nitrous acid. So if that's how much acid that I have, then I need this much of my base, my titrant, in order to reach equivalence point, right? So if I have 0.1 moles of sodium hydroxide, well, how do I convert my way to get the volume of this? Well, we can use molarity, right? 1 mole, we have 1 molar sodium hydroxide, which means we have 1 mole for every 1 liter of sodium hydroxide, right? And then just to be consistent with our volume of nitric acid, which was given in milliliters, I'm going to go ahead and convert this to milliliters. So we have 1 liter on the bottom, 1,000 milliliters on the top. Again, I'm going to cancel my units, make sure everything makes sense. And we have 100, so 0.1 times 1,000, or 100 milliliters of sodium hydroxide. So this is the volume right here, this 100 milliliters here. This is the volume that is required to reach the equivalence point, right? And if you were following along with the equation from the video from last week or last week's live stream, we did a similar problem where we were doing a strong acid, strong base titration. Instead of 100 milliliters of 1 molar nitrous acid, it was 100 milliliters of 1 molar hydrochloric acid. And we got the same exact result. 100 milliliters of base is necessary to react or to reach the equivalence point. So what we're sort of learning here is that the equivalence point doesn't really matter whether the acid is strong or weak. All we're looking at is the volume of that titrant required to supply the same number of moles of titrant as you have of your analyte. So that is the whole point in figuring out the volume required to reach the equivalence point. So, all right, now that we're done with that, I'm going to go ahead and just erase all this stuff. Whoops. Thought I was on the lasso tool. Going to erase all this stuff. Got a couple of messages in the chat from, one's from Kritik Sharma. It says, thank you, sir, for teaching us with your best shot. Excellent. Yeah, thanks for your kind words. Appreciate it, dude. Demeen says, question, can you do the M1 V1 equals M2 V2 with V2 being equilibrium and solve it algebraically? I don't know exactly what you're saying in that question. I'm not sure. Demeen also says, also, thanks again. Last week did help out a lot. Yeah, Demeen, you're one of those real MVPs from last week. I appreciate your participation a week ago. That was pretty awesome. Okay, so what we're going to do now is, okay, we figured out the volume required to reach the equivalence point. That was 100 milliliters. So I'm going to go into my Excel sheet here and just highlight this row here, 100 milliliters. I'm just going to highlight that for the moment, just so that we understand that that's the equivalence point. I'll even write it in EQ for equivalence, right? So that's our equivalence point. So now that we know that, we can get back to solving the first pH value, which is 0 milliliters. So what we're looking at is the initial pH of this aqueous solution, this nitrous acid solution, before we start adding any sodium hydroxide to it, right? So that's what we're looking at. So the initial pH, I'll just say 0 milliliters of NaOH added, right? The initial pH. Well, we've done problems like this before, right? So you have a volume. The volume's not super important, but you have the concentration of a weak acid, and you want to know what the pH of a weak acid solution is. Well, that's a pretty... If you're just now studying aqueous ionic equilibrium, and you've already looked at acids and bases content, and you already have a good understanding of chemical equilibrium, then this problem is actually pretty easy. It's just going to be just a standard equilibrium problem associated with a weak acid reacting in water. So what does that look like? Well, first, the way that you go about solving this is to write the equation for the acid reacting with water, right? And so that would be the following, where we have HNO2, and let me go back, that's aqueous, right? Plus water, that is aqueous, right? Do my equilibrium arrows a little bit better than that. And so what's going to happen? Well, the acid here is going to donate NH plus, a proton, to the water here. And so we're going to get H3O plus, aqueous. And then we're also going to get the conjugate base of the acid. That would be NO2 minus, which is also aqueous. So right, so this is the equilibrium problem. So again, we're not adding any sodium hydroxide here. So this calculation, we've seen calculations like this before many times. So I'm going to go through this, but I'm going to go through it somewhat quickly. If I confuse you or if I go too fast, I have plenty of content both in my chemical equilibrium playlist and my acids and bases playlist, where we do a lot of problems just like these in a much more thorough, much more slow, much more deliberate manner. So I'm going to go through this one pretty quickly. Okay, so we're going to set up our ice table. That's I for initial, C for change, E for equilibrium. Initially, we have 1 molar HNO2, and we have approximately 0 of both of these. The concentration of HNO2 is going to decrease by a value that we can call X, so minus X. At the same time, the concentrations of hydronium and of the conjugate base of nitrous acid are going to increase by that same amount that we're calling X. And so at equilibrium, we have, for HNO2, we have 1 minus X. For the H3O plus, we have X, and we also have X for the NO2 minus, right? So now we have expressions of all of the chemical species in this equation at equilibrium in terms of X. So now what we need to do is we need to be able to equate the equilibrium constant to the products of these concentrations of the products divided by the concentrations of reactants in terms of X. So how do we do that? So let me see if I can, I want to be able to, maybe not resize, but yeah, it'd be nice to be able to resize that, but I don't think I can. Let's see if I can change. I just want to like leave myself enough room without having to erase anything. You know what I'm saying? So I think if I can drag it up here, I can probably leave myself enough room down here. Okay, so and again, at this point, this all should be a review, but I'm doing it again just for the sake of it, because you know repetition is the key to success, right? So we know, right, that I'll do this in. So we know that Ka Now, the numerical value of Ka was given by the problem, but we also know that Ka, the acid dissociation constant, is going to be the concentration of the products divided by the concentration of the reactants. So what are the products? Well, we have our H3O plus, and we have our NO2 minus. And for our reactants, we have HNO2. We can ignore water because water is actually, I don't know why I said aqueous. It should be L for liquid here. My bad. Water is a pure liquid, so its concentration doesn't change, so we don't include it with the equilibrium constant expression. Again, I've said this a million times, but hey, maybe someone hasn't heard it. All right. So the numerical value of that is, which was given to us in the beginning, right? 4.6 times 10 to the minus 4. And so now if we use these equilibrium concentrations in terms of x, we can build this quadratic equation here, right? So the products H3O plus NO2, that's x and x, so I'll just go ahead and rewrite that as x squared, okay? And then for the reactant HNO2, that's 1 minus x, so 1 minus x. I'm going to assume here that the x is small approximation is going to be valid, so I'm going to ignore this from the calculation. I'm just going to cross it out. And again, what I'm doing with this approximation is that I'm assuming that the value of x is much, 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 much smaller than the number from which we are subtracting it. I think that 1 is much, much, much bigger than what the value of x turns out to be, so I am excluding it from this expression. It's called the x is small approximation. Again, this is all stuff that we talked about before, okay? None of this should be a curveball, but just in case it is, that's why I'm briefly explaining it. But if that's not enough, just go back and look at my prior content. So we have x squared over 1, which is simply equal to x squared, right? Is equal to this 4.6 times 10 to the minus 4 term. I'm going to go ahead and delete all that stuff that I no longer need, right? So x squared is equal to 4.6 times 10 to the minus 4, which means that x is going to be equal to the square root of 4.6 times 10 to the minus 4. And we also know that x is, if I could squeeze it in here, that's the H3O plus concentration, right? At equilibrium, according to our ICE table. So the square root of 4.6 times 10 to the minus 4, what is that? Looks like it's 0.021. So we know that the concentration of hydronium ion is 0.021 molar, right? And so we're just one last step away from getting the pH here, right? The pH is equal to the negative log of the H3O plus concentration, right? That's the expression for pH. So since we just calculated the H3O plus concentration, we can throw that in here. So it's the negative log of 0.021, right? Negative log of 0.021. And that number ends up being, okay, I'm a little, I don't know. I don't want to say disappointed because that's too strong a word. But I was kind of hoping that you guys would just fill in some spaces and follow along with me and, you know, type what you have in the chat. If you have a scientific calculator, great. If you don't, I don't know, just let me know. So, all right, so pH is equal to negative log of 0.021, and that number ends up being 1.68, right? 1.68. Player Job says 5. Not quite 5. Not quite 5, but close enough. Not quite 5. All right. So it's 1.68. So what I'm going to do is I'm going to head back into my Excel spreadsheet here, and I'm going to calculate that I'm going to type in that pH value, 1.68. That is our pH of that's our initial pH. Again, before we add any titrant to this, we have a solution whose pH is pretty low, which is what we would expect for a solution of nothing but an acid inside. Even if it's a weak acid, it's going to have a pretty low pH as long as the concentration is fairly high. So, all right, so let's get back to the whiteboard. So we started out with 0 milliliters added. Now we're going to do 10 milliliters. So what happens when we add 10 milliliters, and how do we calculate the pH of such a solution? So I'm going to erase all of this stuff. We no longer... Oh, no. I didn't mean to do all that. Every time I use that eraser tool, I'm always erasing things that I wasn't trying to erase. I think the lasso tool does a better job. All right, so we have 10 milliliters of NaOH. What is the pH going to be of this nitrous acid solution when we add 10 mils of our 1 molar sodium hydroxide. Are you ready to do this calculation? Because I totally am. All right, here we go. So the first thing we need to do is, since we have 10 milliliters of 1 molar NaOH, we need to take that bad boy and we need to convert it to moles. How many moles of sodium hydroxide are in 10 milliliters of a 1 molar solution? That question is pretty easily answerable. We just start out with our 10 milliliters of NaOH. Going to convert that into liters. So for every 1 liter, there are 1,000 milliliters. That's how we perform that conversion. Pretty straightforward, right? And then we can use the molarity of the sodium hydroxide, which is 1 molar, which means we have 1 mole for every 1 liter of this stuff. Make sure our units cancel out. Milliliters, milliliters, liters, liters. And we're left with good old moles, because that's good, because that's what we want. And I just realized that I am in the way of this calculation. So I apologize for that. Just move that down there where it belongs. All right, so what do we have? 10 divided by 1,000, so that would be 10 divided by 1,000, 0.01, right? Yeah, sorry, I got my decimal points mixed up here. 0.01 moles of sodium hydroxide, right? Let me drag this over just a little bit more so I can label this properly. Okay. Darn it. That's not what I was trying to do, guys. All right. I'll just leave it like that. Demeen says 0.01. Yes, you are correct, sir. Okay. So got another message from Kaylee. It says, I did my time for chem, now computer science now. Yeah. I bet you're probably happy to have moved on and put it in the rearview mirror. Well, I have enjoyed having you as one of my viewers, so I hope you do what you're doing now and come by occasionally and say hello. I appreciate that, and I hope you're doing well. Okay, so we just figured out how many moles of sodium hydroxide we're going to throw in there. So now what we need to do is we need to set up a table, and it's not going to be an ice table. It's just a table that helps us track the neutralization reaction between our added base and our existing acid. So what does that equation look like? Well, it's going to look like this, right? Where you start out with your OH, you have your OH minus, right? Hydroxide ion, that represents what you add to it. That's going to react with the HNO2, and that's going to produce water, H2O, and NO2 minus, right? So this is the neutralization reaction. So when you add some hydroxide to it, it's going to convert a stoichiometric amount of the existing HNO2 to the NO2 minus. So what we're going to do is we're going to set up 3 rows. One of them is going to be the conditions before the addition, what the actual addition is, and after the addition. So we have a row for the conditions before the addition itself in the middle, and then another row for the conditions after the addition has been performed, right? So before the addition, well, how many moles of HNO2 do we have? Well, I suppose we should have performed that calculation earlier, but actually, you know what? We did perform that calculation earlier, because earlier we performed, we did the volume required to reach equivalence point calculation, right? And in that calculation, we figured out how many moles of HNO2 we have, and that number turned out to be 0.1 moles, right? 0.1 moles. That's what we have in there additionally. Don't have any NO2 minus, and we're going to add some sodium hydroxide, right? So the sodium hydroxide that we add is this amount. This is what we just figured out, 10 milliliters of 1 molar sodium hydroxide. That's 0.01 moles, right? And so again, that sodium hydroxide, or that hydroxide, to be more accurate about it, is going to convert a stoichiometric amount, or 0.01 moles of this existing HNO2 to the NO2 minus. So after the addition is complete, the amount in moles of this stuff is going to decrease by this value, 0.01, and so we're left with 0.09 moles of our HNO2, and then over here, we're going to end up with 0.01 moles of NO2 minus, right? So again, that added hydroxide is converting a specific stoichiometric amount, in this case 0.01 moles of the HNO2 to the NO2 minus, right? So now we have the amount in moles of HNO2 and its conjugate base, right? So this is a situation in which we have an aqueous solution that has significant amounts of both a weak acid and its conjugate base. I'll say that again. An aqueous solution that consists of significant amounts of a weak acid and its conjugate base. Isn't there a name for that type of aqueous solution? Yes, there is. It's called a buffer. This is a buffer solution, right? Significant amounts of weak acid and its conjugate base. That's called a buffer. And earlier on in this live stream playlist series, we looked at how to calculate the pH of a buffer solution very, very easily. It's called the Henderson-Hasselbalch equation, right? Anybody remember what the Henderson-Hasselbalch equation looks like? Not a rhetorical question. Really want somebody to answer that. Don't see anybody answering it. All right, I'm going to go ahead and write it in anyway. So the Henderson-Hasselbalch equation is the pH is equal to the pKa of that weak acid plus the logarithm of the concentration of your base divided by the concentration of your acid. And I really need to look at this and make sure that I'm not in the way, which it looks like I am again. Hang on. I'm going to drag the equation a little bit closer to you. There it is. Yeah, Damien just pointed it out. pH equals pKa plus log of concentration of base over concentration of acid, right? That's the Henderson-Hasselbalch equation. And it can only be used when you have a buffer solution, in which you have a solution with significant amounts of a weak acid and its conjugate base. In this case, we do have such a solution, so we can use this formula to calculate the pH, right? So what's the pH going to be? It's going to be, well, pKa, we know what that is, right? That was given by the problem. pKa is 3.34, according to the problem. Oops, 3.34. plus the log of concentration of base over concentration of acid, right? The base, we have 0.01 moles. Acid, we have 0.09 moles. I'm going to go ahead and fill that in. So we have 0.01 moles. I'll do that a little closer. 0.01 moles over 0.09 moles, right? So pH equals 3.34 plus the logarithm of 0.01 divided by 0.09. That is how we're going to get our pH from this. And again, this only works when we have a buffer solution, but in this case, we just happen to have a buffer, so we can use that Henderson-Hasselbalch equation. 3.34 plus the log of 0.01 divided by 0.09. Has anybody calculated that? Value that I got was 2.39. 2.39. Looks like Damien got the same thing, man. Damien, you are crushing this, man. You guys should all take a page out of Damien's book. He or she, I can't remember if you're a lady or a man, are crushing this right now, and I'm so proud of you. Good job. All right, so 2.39. So I'm going to hop back into this Excel spreadsheet here, and I'm going to input that into this. This is 2.39. So that was the pH when we added 10 mils of our 1 molar sodium hydroxide to our 100 milliliters of 1 molar nitric acid. So the next one that we're going to do is for 20 mils. So I'm going to go ahead and go back to the whiteboard and erase all the stuff that I no longer need. So I can erase that. I can erase that. And I'll just replace that one with a 2. 20 milliliters of sodium hydroxide. What is the pH going to be of the solution when we perform that addition? That is the question. I got another message from Kaylee. Says, yeah, sorry, I haven't been around. We moved, school started, and I'm pregnant. So, oh my goodness, congratulations. Everybody here, let's just take a little break from the chemistry for just a second and all congratulate Kaylee. That is wonderful, wonderful news. I wish you the absolute best in terms of the pregnancy and the health of your baby, and I think that's awesome. So congratulations for that. Okay, so back to chemistry, since this is a chemistry show here. All right, so 20 milliliters of added sodium hydroxide. What's the pH going to be? Well, again, we need to take our 20 milliliters and convert that into moles, right? So 20 milliliters I'll do this in black, 20 milliliters of NaOH, right? 20 milliliters of NaOH. Got to convert that into liters, so we have 1,000 milliliters on the bottom, 1 liter on the top of this conversion factor. Then we're going to use molarity to calculate the number of moles. So we have 1 liter on the bottom, 1 mole on top. That's what a 1 molar solution means. Just canceling out my units, make sure this is definitely correct, and I get 0.02 moles of sodium hydroxide, 0.02 moles of sodium hydroxide. So when I perform this sort of calculation here, where I'm keeping track of before, after, what the addition is, and after, the amount that I add is going to be 0.02 moles of sodium hydroxide, right? So we have 0.02, that's the addition, which means that our nitrous acid is going to decrease, the amount of nitrous acid is going to decrease by 0.02 moles. That's going to be 0.08 moles. And again, that's 0.1 minus 0.02 equals 0.08. And meanwhile, that's going to be that 0.02 moles that we lost of nitrous acid is going to be converted to the nitrite ion, NO2 minus. So that's 0.02 moles, right? And so at this point, we can simply use that Henderson-Hasselbalch equation once again to solve for pH, right? So if I could squeeze it in down here, so pH is equal to pKa plus the log of concentration of base over concentration of acid. In this case, we have 0.02 moles of base, we have 0.08 moles of acid, and then for pKa, of course, that's the 3.34. That was just given, right, by the problem. 3.3, different shade of purple, my bad. 3.34. So this is at 3.34 plus the logarithm of 0.02 divided by 0.08. That is the mathematical expression that's going to get us to pH. So if anybody wants to calculate that, you're more than welcome to. I'm going to go ahead and calculate it real quick too, and so I can make sure we all got the same thing. 0.34 plus, oops. Make sure I got the right. Yeah, this should be right. All right, the number that I got, since nobody else seems to want to participate at this point, which is okay, I understand, is 2.74. 2.74, that is the pH when we add 20 milliliters of 1 molar sodium hydroxide to our 100 milliliter solution of 1 molar nitrous acid. So I'm going to go ahead and go to my spreadsheet here and just drop that in there, 2.74. Okay. Now the next point of the calculation, the next volume of sodium hydroxide that we're going to look at is 50 milliliters. 50 milliliters of sodium hydroxide. So let me go back to the whiteboard here. So bear with me for just a moment. I'm going to erase everything that I no longer need. Don't need that. Don't need that. Don't need that. And I don't need all that stuff. Missed some things. Okay, so we're looking at now 50 milliliters of sodium hydroxide. So what is that going to look like? Well, again, we're going to have to take that 50 mils and convert it into moles of sodium hydroxide. So we have 50 milliliters of sodium hydroxide. Since it's in milliliters, we need to convert it to liters to be compatible with molarity. So 1,000 milliliters are in 1 liter. And then the molarity of the sodium hydroxide solution has been conveniently chosen to be 1 molar. That means we have 1 mole for every 1 liter of NaOH. Sure that our units cancel. Milliliters, milliliters, liters, liters. Okay. So now we have 0.05. 50 divided by 1,000. So we have 0.05 moles of sodium hydroxide are are going to be added to this stuff, right? Very good. Yeah, 0.05, not capital M, it's just MOL, right? 0.05 moles, not 0.05 molar. There you go. There you go. There it is. Nice. Very cool. All right. So again, initially we have 0.1 moles of our HNO2. That's just a calculation that we've done long ago. It just always applies with every single point in this titration. This is always applicable, right? And so the addition of sodium hydroxide in this case is going to be 0.05 moles, right? And again, this equation and this table, what do they represent? They represent the hydroxide coming in and converting a stoichiometric amount of the existing nitrous acid that's in there to the conjugate base of that acid, the nitrite ion, right? And so the amount of HNO2 decreases by 0.05, so we end up with 0.05 moles of it, and then we end up with 0.05 moles of the conjugate base of the acid also. So instead of just squeezing my Henderson Hasselbalch down here, I'm just going to delete this stuff so that I have more room for my Henderson Hasselbalch equation up here. Sorry, my computer is really lagging right now. I don't know if I just got too many things open or what. Okay, so again, I'm going to use the Henderson Hasselbalch equation here. It's going to be pH equal to the pKa, which in this case is 3.34, plus the logarithm of concentration of base over concentration of acid. Base is 0.05, and acid is 0.05. So Demeen says, did we calculate the equation yet? I forgot, not going to lie. Oh, no, you're good, man. Yeah, we're working on it right now. All right, so log of 0.05 over 0.05. Well, we know that 0.05 over 0.05 is equal to 1. Anything divided by itself is 1. Pretty basic mathematics there. But what's the logarithm of 1? And again, with a logarithm, what you're doing is you're asking yourself, what power do I have to raise 10 to get what's inside of that logarithm? So what power do I have to raise 10 to get to 1? Well, it's 0, right? It's 0. So the pH, in this case, this whole thing can be canceled from the equation. So the pH in this case is equal to 3.34, which is the same thing as the pKa of the acid. And this has a name. It's called the half equivalence point. So I'll go ahead and write that in, half, or just 1/2 equivalence point, right? So at the half equivalence point, the concentrations of base and acid are the same, and therefore they cancel each other out in that Henderson-Hasselbalch equation, or it ends up being a value of 0 for that logarithm term, and so the pH is equal to the pKa. So I got a message from Kitty B. It says, hey, I wish I could stay for the whole stream, but I can't. Thank you so much for what you do. Can't wait to go back to this vid later. Oh, well, listen, just the fact that you were able to stop by and leave that comment means the world to me. Totally understand, Kitty. I hope you are all set up to have a great week, and I hope you've had a great weekend. Again, thank you. All right. So 3.34, that's the pH when we added 50 mils of our 1 molar sodium hydroxide to our 100 molar, 100, or not, did I say 100 molar? 100 milliliter, 1 molar sample of nitrous acid. Sorry, I'm confusing myself. So I really don't want to confuse, definitely don't want to confuse you guys. So I'm going to go back to my Excel spreadsheet here. Just type that in, 3.34. So that's our half equivalence point. I'm just going to highlight that another color real quick just to sort of let that stand out. So this 50 milliliters, that's the half equivalence point. All right, so we're going to move on. The next volume that we're going to look at is 80 milliliters. So I'm going to go back to my whiteboard here. So the question again that I'm essentially asking myself is, what is the pH of an aqueous solution whose initial concentration of nitrous acid is 1 molar, there's 100 milliliters of it, and I add 80 milliliters of 1 molar sodium hydroxide. That was kind of a mouthful, but I don't know, in order to accurately represent what's going on, I kind of had to use a lot of words, so kind of can't really avoid a mouthful when you're talking about this kind of stuff. All right, so I'm going to erase all this stuff that no longer applies. Okay, 80 milliliters, 1 molar sodium hydroxide. Got to convert that sucker to moles once again. So we have 80 milliliters of NaOH. Whoops, not trying to zoom in like that. This pen has like buttons on it. I think I hit one of the buttons by mistake. Edward Cho says, also need to go, but wanted to say thank you for your work. You're always a great help. No cap. Awesome, man. Thank you, Edward. And same goes for you. I hope you've had a great weekend, and I hope you are all set up to have a great, awesome, productive week. Thank you again, and take care. Appreciate you being here. All right, so we have 80 milliliters of our sodium hydroxide. That's going to be converted into liters, right? 1,000 milliliters on the bottom, 1 liter on the top. Going to use the molarity of the sodium hydroxide solution again to convert to moles. We have 1 moles on top, 1 liter at the bottom. Milliliters cancel, liters cancel. We have 80 divided by 1,000, which is equal to 0.08 moles of our NaOH, right? And so this table here, we start out with our 0.1 moles of HNO2. We're going to add 0.08 moles of sodium hydroxide. So that 0.08 moles, that is the amount by which the amount of HNO2 is going to be reduced, right? So it's going to be 0.1 minus 0.08, ends up being 0.02 moles. And that 0.08 moles is then going to be converted into the conjugate base, right? The nitrite ion, 0.08 moles. And then just like we did in the previous couple of examples, we can simply use the Henderson-Hasselbalch equation to solve for the pH. Isn't the Henderson-Hasselbalch equation just the best thing? You don't have to do all these like crazy equilibrium problems and stuff with the common ion effect and everything. God, I love the Henderson-Hasselbalch equation. It just saves me so much time. I don't know who Henderson and Hasselbalch are, but I mean, wherever you guys are, I salute you. Okay, the pH is equal to pKa plus log of base over acid. So pKa, that's 3.34, plus the logarithm of a concentration of base, concentration of acid. So concentration of base is 0.08. Actually, that's the amount in moles, but same difference. Concentration of acid, 0.02. So you might be asking yourself, like, well, 0.08 and 0.02, those aren't the concentrations of acid and base. Those are simply the amounts of the acids and base, the acid and the base in moles. And while that is true, the volumes cancel out because both of these quantities of acid and base are in the same solution. So by definition, they have the same volume. So whether we're using a ratio of concentrations or a ratio of the amounts, it doesn't matter because they equate. They are the same value. So I just wanted to make sure, we all understood that. Like in this equation, you can use the amount in moles. You don't necessarily have to convert that amount into concentration for this equation to work. I'm stalling while somebody calculates this. I know you guys have it in you. Blair Job says it's Hasselbalch in my head. Oh, isn't it like a quarterback for the Seattle Seahawks or something? I can't remember. pH of 3. Let's see. Okay, let me calculate it real quick just so that I can with you guys here. I have it written down, but yeah, it looks like we got the same thing. So, all right, yeah, I got the same thing. So I'm gonna just go ahead and write it. 3.94. So 3.34 plus the log of 0.08 over 0.02. That's 3.94. So once again, going to go over to my handy dandy Excel spreadsheets. Going to put that in 3.94. I like the idea of using Excel and showing like tutorials on how to use Excel as a chemist and like sort of like what some of the functions and things that you can throw in there into a spreadsheet to make it really valuable and useful to a chemist. So if you guys think that'd be something you're interested, let me know in the chat or in the comments, whether you're watching this live or as a video, and maybe that's something I can do. I think that would be pretty cool. I just have to like figure out how I'm going to do it, but I think that'd be cool. All right, so next one is 100 milliliters. So this is the equivalence point as we have previously established, right? So we're going to calculate the pH of this aqueous solution at the equivalence point. So how exactly are we going to do that? So that's what I'm going to show you guys. So, all right. So this is going to be a pretty long-winded calculation, so prepare yourself accordingly. Maybe go to the bathroom right now if you need to. All right. We have 100 milliliters of 1 molar sodium hydroxide. So let me ask you guys something in the chat. So at the beginning of every one of these calculations, I always like convert this volume of sodium hydroxide into moles, and it's pretty repetitive. And if it's okay with you guys, I'd like to just jump to the moles of sodium hydroxide. In other words, just do that conversion in my head. If the answer is no, that's fine. Like, I can do them all by hand. But I would like some feedback on that, because I don't want anybody watching the stream like, oh my god, he's going to convert the sodium hydroxide to moles again. He's already done that like 5 times. How much longer this shit do we have to sit through? You know what I mean? Like, I don't want to bother you guys with that. So this is like where I really want your answer here. What do you think? Should I convert the volume of sodium hydroxide to moles every time? Or can I occasionally skip that step? Dumeen says, no, please, I'm a steps person. Okay, that's good feedback. All right, I'll keep doing it. All right, so we're adding 100 milliliters of 1 molar sodium hydroxide. So we start out with our 100 milliliters of NaOH. We're going to convert that into liters, just as we have done previously several times, right? So we have milliliters on the bottom, liters on the top, 1 liter on the top, 1,000 milliliters on the bottom. Then we're going to use the molarity of the sodium hydroxide. Of course, it's 1 molar, so that means there's 1 mole for every 1 liter, right? Make sure that our units cancel, and they do. And we are left with 100 divided by 1,000, which is 0.1 moles of sodium hydroxide. 0.1 moles of sodium hydroxide. So we're going to take that value, that 0.1 moles, and we're going to sort of bring it to this table here, like we've done before. So we're adding 0.1 moles of sodium hydroxide. That means that this is going to deplete all of the nitrous, I keep saying nitric. This is going to deplete all of the nitrous acid in this buffer. It's going to take the entire amount, that 0.1 mole, and it's going to convert it to NO2 minus. So at the end of this addition, we have 0 moles of HNO2, and we have 0.1 moles of NO2 minus, right? So that's kind of interesting. So essentially what we've done here is we've destroyed the buffer, right? Because as long as there was a significant amount of a weak acid and a conjugate base in there, it could be relatively resistant to changes in pH. But now that we've destroyed that buffer, as we'll see in the calculations to come, the pH is going to rise dramatically in response to even a little bit more added titrant. So, okay. So this solution now is no longer a buffer. So earlier, when we had both significant amounts of weak acid and conjugate base, we were able to use the Henderson-Hasselbalch equation to solve for pH, but that doesn't apply anymore. We don't have any weak acid. We only have weak base. So the Henderson-Hasselbalch equation is useless to us in this context. So how on earth are we going to calculate the pH with just 0.1 moles of NO2 minus? Well, we can use the principles and the knowledge that we have of chemical equilibrium and acid-base equilibria, just like we did at the very beginning of this discussion, to work our way to that calculation. It's going to be pretty long-winded, so I'm going to let me just sort of whoops, I didn't mean to do all that. Let me just kind of scroll to a clean, like, fresh part of the whiteboard here, because again, I'm gonna have to do like a lot of calculations here. So, yeah, I'm trying. I'm sorry, guys. I'm just trying to figure out a good way to do this. All right. All right. Well, before we do that, let's get some things sort of straightened out. So what we're going to be doing is we're going to be setting up just like an equilibrium problem. We're going to write the chemical equation associated with a base reacting in water to produce its conjugate acid and the hydroxide ion. We're going to use equilibrium to solve for concentration of hydroxide. We can calculate POH from that, and then we can calculate pH from the POH. Now, I know that was a mouthful, but one thing that we need to understand here is that the concentration of NO2 minus, right? Concentration of NO2 minus, that's going to be equal to the amount of it divided by the total volume, right? The amount of it divided by the total volume. So the amount of it we just figured out, 0.1 moles, right? 0.1 moles. But what's the total volume? Well, initially we start out with 100 milliliters of solution. We added 100 milliliters of solution to it. So we really have 200 milliliters of volume in total. So this is going to be 0.2 liters. And I've converted that 200 milliliters into liters in my head just to make sure that we're in liters so that we can calculate the molarity, the molar concentration of NO2 minus, right? So if you take 0.1 divided by 0.2, that's 0.5 molar, right? So what we're going to be doing is we're going to be finding the pH of a 0.5 molar solution of this nitrite ion, right? So how do we do that? Well, the first thing that we're going to do, whoops, keep doing that by mistake. The concentration is 0.5 molar, so I'll sort of leave that in view here. So the first thing that we're going to do is we're going to just simply write the chemical equation for the reaction, right? So we have NO2 minus, that's the nitrite ion, that's aqueous, reacting with water, which of course is a liquid, to produce the hydroxide ion, that's OH minus, and that's aqueous. And we're also going to get, if I can pull this over a little bit more, we're going to get the conjugate acid of nitrite ion, which of course is HNO2, aqueous, right? So again, all we've done here is just wrote the equation associated with the reaction of nitrite ion with water. The nitrite ion acts as a base, accepting a proton from water. The water acts as an acid, donating a proton, and so you're left with hydroxide, which is basically a water molecule after donating a proton, and you're left with the nitrous acid, which is the same thing as nitrite ion after gaining a proton, right? So going to set this up like an ice table. So we're going to have I for initial, C for change, E for equilibrium. Now, as a moment ago, we established that our concentration of nitrite ion is 0.5 molar, right? And so initially, we have 0.5 molar nitrite ion. We're going to assume that we have essentially no OH minus and no HNO2. The change, well, that's going to be minus a certain value, which we'll call X in the case of the reactant here. And then the products will increase. The concentrations of the products will increase by the same amount by which the reactant concentration is decreasing. And then at equilibrium, we have 0.5 minus X in the case of NO2 minus, and then we simply have X and X for hydroxide and nitrous acid. It's a bad habit. Keep saying nitric acid when I mean nitrous acid. I need to stop. All right. So now what are we going to do? Well, we can, what we need here is the Kb, right? We need the base dissociation constant or base ionization constant for NO2 minus, right? And so the thing about conjugate acid base pairs is that, and again, a conjugate acid base pair, that's just two substances who only differ in the gain or loss of a proton, right? Of an H plus. The thing about conjugate acid base pairs is that if you have Ka, right, for the acid and Kb for the conjugate base, the product of those is equal to Kw. And again, the Kw, that's the ion product constant for water, right? That is the equilibrium constant that describes a neutral solution of acid and base where the concentrations of hydronium and of hydroxide are equal. And I just realized I am off the page again. Man, I need to have like somebody like on Discord, like in my ear, telling me like, "Hey, dude, like move the text. It's like you're in the way. You're just." Sorry, guys. I'm just clueless tonight. Okay. So again, the goal here is we're trying to get Kb for NO2 minus. And what I'm trying to grasp at here is that we can get Kb for the we can get Kb for the base as long as we know Ka for the acid. We can calculate it using this relationship here where Ka times Kb is equal to Kw, right? So Kb then is going to simply be Kw divided by Ka, right? And those are both known quantities. Kw at 25 degrees C is 1.0 times 10 to the minus 14. And Ka, well, that was sort of given by the problem, right? Ka, 4.6 times 10 to the minus 4. Here it is. right here, 4.6 times 10 to the minus 4. So I'm just going to go back here real quick to the part of the whiteboard that we're working on right now. Okay, what did I say? 4.6 times 10 to the minus 4? Yeah, 4.6 times 10 to the minus 4, right? And so this is, once we solve that, we'll have KB, so we'll have everything we need to calculate the concentration of hydroxide from this equilibrium problem, right? So give me just a moment. I'm going to perform this quick calculation. So 1 times 10 to the minus 14 divided by 4.6 times 10 to the minus 4 equal to, what I got was 2.2 times 10 to the minus 11. 2.2 times 10 to the minus 11 is what I got, right? So now we have KB. And again, let me sort of drag this a little bit better for you guys. See if I can zoom out just a little bit. Yeah, there it is. 2.2 times 10 to the minus 11, that's the KB. So we know that 2.2 times 10 to the minus 11, write that a little bit better. 2.2 times 10 to the minus 11, we know that that's going to be equal to the concentrations of the products over the concentrations of reactants at equilibrium, right? And so for the products, we have X and X, right? So X times X, I can rewrite that as X squared. And then for the reactant, we have 0.5 minus X. I'm going to assume that the X's small approximation is valid here and just ignore this X, just omit it from the calculation. And again, what I'm doing is I'm assuming that this value is very, 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 very small compared to 0.5, which is what we're subtracting it from, right? So I'm just going to ignore that from the calculation. And so we have X squared over 0.5 is equal to this thing over here, 2.2 times 10 to the minus 11. So let me take this equation here and drag it into a more centrally located location so I can more easily manipulate this equation, right? So that means that X squared is going to be equal to the product of 2.2 times 10 to the minus 11 and 0.5, right? All I did was just multiply 0.5 by both, or multiply both sides of the equation by 0.5 to get this, right? So X squared equals this product right here. And then to solve for X, all I need to do is to take the square root of that. So I'm going to take the square root of that. So this is the expression here. It's the square root of the product of 0.5 and 2.2 times 10 to the minus 11. That's what X is equal to. And in this context, X is equal to the OH minus concentration, right? That's what we're trying to figure out, because from there we can get POH and from there we can get pH. It's a long way to the end of this calculation, but that's kind of how it works whenever you have a base that you don't know it's KB, but you have to figure it out using K and KW, and you have to do all this equilibrium stuff. It's just what you have to do. So you either complain about it or just do it, right? Okay, so what is this value? What did I get? I got a value of, and again, this is the hydroxide ion concentration. I got a value of 3.3 times 10 to the minus 6. 3.3 times 10 to the minus 6. That is the concentration of the hydroxide ion in this problem here, right? 3.3 times 10 to the minus 6. So from there, well, we can't get pH directly, but we can get POH, right? We know that POH, let me do this in another color here. POH is equal to the negative log of the hydroxide ion concentration, right? So in this case, negative log of this whole thing right here, negative log of 3.3 times 10 to the minus 6. So negative log of 3.3 times 10 to the minus 6, right? And so that value ends up being, I got 5.48. 5.48, that's our pOH, and then we also should know at this point that the sum of pH and pOH is equal to 14. And this is assuming we're at 25 degrees Celsius, which is all of my acid-base stuff. Unless I say otherwise, I'm talking about 25 degrees Celsius because it's the most commonly reported temperature for these types of problems. All right, so we know that pH is simply going to be 14 minus the pOH, right? So pH is going to be equal to 14 minus the pOH. In this case, that's 5.48. And so finally, our pH ends up being 8.52. 8.52. So let me hop into the spreadsheet here and just populate the appropriate cell with that, 8.52. So that's the pH at our equivalence point. So I think it might be worthwhile to sort of backtrack a little bit and just kind of went over all of the parts of how to solve that problem, because it was a very, very lengthy problem. I'm not going to say it was difficult, but it was just very lengthy. There was a lot of parts to it. So I want to make sure we understand that. So again, we started by simply converting our added sodium hydroxide here into moles, right? So we used that to figure out that we added 0.1 moles of sodium hydroxide to this, right? And then we understood through this table here that all of the weak acid, all of the HNO2 was converted into NO2 minus its conjugate base. And so now all of a sudden we're dealing with a 0.5 molar solution, right? Because we took that 0.1 moles and divided it by the total volume, which was 200 milliliters. And all of a sudden now we have a 0.5 molar solution of nitrite ion. And so we have to use chemical equilibrium to get the concentration of hydroxide for that, which is exactly what we did. We calculated the Kb using the Ka times Kb equals Kw relationship. And then we invoked the principles of equilibrium that we've hammered time and time again throughout this last several weeks of this live stream in order to get the concentration of hydroxide. Once we had concentration of hydroxide, we got pOH from that by taking a negative logarithm of it. And then we understood that pH and pOH add up to 14. And so we were able to use that to finally get our way to pH. So, yeah. Big problem. Very, very big problem. A lot of moving parts in that one. So I'm going to set up for the next one here. So I'm just going to erase all this stuff here that we no longer need. Don't need that anymore. Don't need that anymore. Didn't mean to do that. What else? Those no longer apply. And I don't need this anymore either. All right. So let me go back to Excel real quick just to see what my next volume is. 110 milliliters. Okay. So we want to know what the pH of this solution is going to be. Look at our curve, by the way. Look at how it just shot up, and now we're at the equivalence point. It's really, really rising rapidly. Probably should have pointed that out earlier, but whatever. All right. So going back to the whiteboard here. So 110 milliliters. So we want to know what the pH of this solution is going to be when we add 110 milliliters of 1 molar sodium hydroxide to it, right? Okay, so we'll start by taking our 110 milliliters of sodium hydroxide and converting it to moles. And again, we'll just use that two-step conversion where we convert from milliliters to liters and then from liters to moles. 1,000 milliliters in 1 liter, 1 mole per liter for a 1 molar solution. Units cancel out just fine, and we are left with 0.11, 110 divided by 1,000, 0.11 moles of NaOH. Okay, so that's how much sodium hydroxide we're going to add to this, right? And it looks like I'm off the page once again. There we go. Something happened just now. I just heard a noise. Did anybody else hear that? I just heard like a ring, gling, gling noise. I don't know what it is. But It sounded cool. So, oh, I just heard another one. Let me know if you guys can hear that, because I don't know if you guys can hear that or not, but it's very, very loud and distracting, but it sounds cool. It's a cool noise. All right, so 0.11 moles of sodium hydroxide. That is what we're adding. So the addition here is 0.11 moles. And so, again, 0.1 mole of that is going to be converted into the conjugate base. So we end up with 0.1 moles of the conjugate base, because that's all the weak acid we have. And then we're actually going to end up being left with some hydroxide ion at the end of this, right? So we end up with 0.01 moles. So this is kind of interesting, because at this point we're adding like more than enough sodium hydroxide, more than enough hydroxide to react with all of the weak acid that we have. So this is like more than enough to destroy the buffer, right? We're adding more than enough of that strong base to destroy the buffer and deplete all of the weak acid that's in there. Actually, it wasn't a buffer before we had any weak acid in it, but you don't understand what I'm saying is that we depleted all of the HNO2 in this. And so we're left with nothing but the hydroxide ion and the nitrite ion, the conjugate base of that acid. And so you might be looking at this thinking that's weird. Well, we have two sources of hydroxide, right? We have just the plain old OH minus that's left over because not all of our weak acid, or our weak acid couldn't react with all of it. And then we have another source of hydroxide here, this NO2 minus. That behaves as a base, as we just recently established in the last problem there. So how do we calculate this? How do we find the pH of this type of solution? Well, if you think about it, right, NO2 minus, that's a weak base. OH minus, that's really, really strong. That's like the strongest that's the strongest base that can exist in water. Anything stronger than OH is converted into OH minus, right? And so what happens here is, and I'm going to highlight this, is that the acidity and basicity of this solution is dominated by the hydroxide. This contributes so much more to the hydroxide concentration than this does that we can essentially just ignore the NO2 minus entirely from the calculation and not incorporate it at all. Again, because it contributes such a small, negligible amount to the overall OH minus concentration compared to the OH minus that we added in there, or the leftover OH minus that's in there after 0.1 moles of it got consumed by the nitrous acid. Okay, so really all we have to do is calculate concentration of hydroxide from this 0.01 moles, right? So how do we do that? Well, I think I can, yeah, I can delete this. Just gonna erase some of this stuff. So we want to know what the concentration of OH minus is, right? That's going to be equal to the amount of it in moles, which is 0.01 moles, divided by the total volume. The total volume is not 110 mils. That's how much we added. We need the total volume, which includes not only the volume that we added, but the original volume before we added anything. It's going to be 100 plus 110 milliliters, which is 0.210 liters, right? So that's 210 milliliters converted into liters, right? And so now the concentration of hydroxide ends up being 0.01 over 0.21. Let me calculate that one real quick. 0.01 divided by 0.21. That ends up being 0.0476 molar. 0.0476 molar is what I got. And then in order to get, we can get POH from that, right? POH is going to be negative log of the concentration of hydroxide ion, so negative log of 0.0476. So that is what exactly? Let me type that in. Negative log 0.0476. 1.32 is what I got. And so, yeah, 1.32. And so if we take, we understand that the sum of pH and POH is 14, right? And so 14, or excuse me, pH is going to be equal to 14 minus the pOH, 14 minus 1.32, and that is equal to 12.68. 12.68. That is our pH. So let me go ahead and type that 12.68 into the spreadsheet here. So yeah, so now that we're past the, especially now that we're past the equivalence point, we've added so much base to this buffer that there's not any there's no longer any acid in there that's going to convert any of the strong base that we add to it to the weak base, or the conjugate base of that acid. So, all right, the next volume that we're going to do is 120 milliliters. And for the next couple of them, they're all going to be very, very similar now that we've sort of passed that equivalence point. But I think it's worthwhile to work them out anyway. So here we go. All right. Go back to the whiteboard real quick. See what I can erase here. Whoops. Try to get fancy. Got rid of most of that stuff, but not all of it. All right, so now we're going to do 120 milliliters. So when we add 120 milliliters of 1 molar sodium hydroxide, what does the pH of this solution end up becoming? That is the question. So again, we start out with 120 milliliters of NaOH. Going to perform that two-step conversion in which we convert it to moles by converting from milliliters to liters and then from liters to moles. 1,000 milliliters in a liter. Since it's a 1 molar solution, we have 1 mole for every 1 liter of solution. Milliliters cancel, liters cancel. 120 divided by 1,000. That ends up being 0.12 moles. And give me just a second here. Just want to make sure. Yeah, 0.012 moles of sodium hydroxide, right? So we're going to take that number, that 0.12, going to throw it in here. 1, 2, that's how much hydroxide that we add, right? So it looks like all of our nitrous acid is going to be consumed, leaving us with 0.1 moles of NO2 minus. I don't know why I wrote that in. And then since only 0.1 moles of this 0.12 moles was consumed by the nitrous acid, that means at the end of this we have 0.02 moles of hydroxide ion remaining. For reasons that I discussed earlier, the hydroxide ion dominates the acidity and alkalinity of this solution in ways that the nitrite ion could only dream of. So this contributes negligibly to the pH calculation. So we're just going to consider this 0.02 moles of hydroxide. So we need to convert that into the concentration of sodium hydroxide. So concentration of OH minus is then going to be 0.02 moles of it divided by the total volume, right? Total volume would be the 100 milliliters that we had initially plus the 120 milliliters of sodium hydroxide that we threw in. So that would be 0.220 liters. So that would be what? 200, yeah, that'd be 220 milliliters, and that's just converted it into liters. So let me calculate that real quick. 0.02 divided by 0.22. Looks like it's 0.0909. That 9 is pretty far away from that 0 there. Fix that. 0.0909 molar, right? That's the concentration. We can get pOH from that. pOH is equal to negative log of the hydroxide concentration, so negative log of 0.0909. So what does that end up being? Negative log of 0.0909. 1.04. So the pH will then be 14 minus 1.04, because the sum of pH and pOH always equal 14, assuming you're talking about 25 degrees Celsius, which we are. So 14 minus 1.04. Clear. Putting that in my calculator, I got 12.96. 12.9. All right, I'm going to throw this into my spreadsheet here. So I'm going to go back here, 120 milliliters, 12.96. Looks like you're correct again to me. Good job. Very cool. What do you need me for? You're getting all these right. I'm just kidding. Thanks for being here. All right. All right, so we've got two more to do. We're going to do 150 milliliters and 180 milliliters, and then we're going to be all done for the night. So, again, thank you to everybody who's in here and those who have participated. Thank you for your participation. It is highly appreciated. And again, if you're watching this as a video later on, leave me a comment. I'd like that. Okay, so 150 milliliters. That's what we're doing now. Back to the whiteboard. Erase all the stuff I no longer need. Yeah, that worked pretty well. Okay. Dab that. 150 milliliters. So, again, we're going to take that 150 milliliters of sodium hydroxide. We're going to convert it into moles using that two-step conversion in which we convert from milliliters to liters and then from liters to moles. There are 1,000 milliliters in 1 liter. There is 1 mole in 1 liter of this 1 molar solution. So the units cancel, and we end up with 0.15 moles of sodium hydroxide. 0.15 moles of it. We're going to take that number. That's going to be the addition here, 0.15 moles. So as you can see, just like in the previous examples, we have more than enough of our hydroxide here to consume all of our HNO2. It's going to convert all of that HNO2 into its conjugate base, right? So we end up with 0.1 moles of that. And then, so the question then is, how many moles of hydroxide were consumed by the nitrous acid? Well, 0.1 moles. And so if you take this 0.15 moles and you subtract the 0.1 moles from it, you end up with 0.05 moles of hydroxide ion. And again, these two sources of hydroxide ion are very, very different from one another. The hydroxide being a strong acid with 100% conversion, or did I say strong acid? I meant strong base. Being a strong base contributes way more to the hydroxide concentration than the nitrite ion does, and so therefore we can ignore it from the calculation, and this can be the only source of hydroxide that we consider, mathematically speaking. Okay, so I'm gonna erase some more stuff here. Let's see. So how do we get the concentration of hydroxide? Well, all we do is we take the amount in moles of it that we just figured out, 0.05 moles. We divide that by the total volume. So the total volume is 100 milliliters plus 150 milliliters, so 250 milliliters, or simply 0.25 liters. I've just converted that to liters in my head so that we can get a molarity out of this, moles per liter. So that ends up being what? 0.05 divided by 0.25. Should be just 0.2, right? Yeah, 0.2. I always make sure I do it in the calculator, even if it looks obvious, just because, I don't know. I'm just that kind of, I always have to type everything in the calculator. Anyway, so we had 0.2. I'll just give it another sig fig. Yeah, who cares? Okay, so 0.2 molar is our concentration We can get POH by taking the negative log of our hydroxide concentration, so negative log of 0.2. The POH ends up being POH ends up being 0.699, and so pH is going to be equal to 14 minus 0.699, again, because the sum of pH and POH is equal to 14. So 14 minus 0.699. I'll just do this to 2 decimal places. Ended up getting 13.30. 13.30. Oh, we got different values to mean. I don't know what's going on. Might be like a rounding error or something. Hang on. Let me get to the bottom of this. Hang on. Yeah, it's I got 13.30. I did it twice, so okay. Yeah, now we got the same thing. Okay, cool. Okay, so 13.30. So let me go into spreadsheet here. So 13.30. Of course, Excel likes to take my 0 that I deliberately put in off of there. So 13.30. All right, so as you can see, our titration curve is kind of taking its shape here, where we have like this, slow climb upward, and then it starts climbing upward very, very rapidly near the equivalence point. And then once you go a certain distance past the equivalence point, it sort of starts to tail off and level off again. Same thing sort of happening here as when we had our strong acid, strong base titration a week ago. But it looks like we have one more to do, so that's 180 milliliters. So I'm going to go ahead and get started on that. So grab everything I need here and delete it. Or everything I don't need, rather. Grab everything I don't need and delete. Okay. $180 milliliters. This is our last one. 180 milliliters of 1 molar sodium hydroxide. What is going to be the pH when I add that to 100 milliliters of 1 molar nitrous acid? All right, so start out with our 180 milliliters of sodium hydroxide. Going to perform that 2-step conversion that allows us to convert from milliliters all the way to moles by converting from milliliters to liters and then from liters to moles. 1,000 milliliters are in 1 liter, and since it's a 1 molar solution, we have 1 mole per every 1 liter. Make sure my units cancel out here, and I end up with 0.18 moles of NaOH. 0.18 moles of sodium hydroxide. I'm going to take that value and throw it down here because that's how much I'm adding to this nitrous acid solution, right? 0.18 moles. So we have more than enough sodium, or more than enough hydroxide to react with all of our nitrous acid. So our nitrous acid, all of it is going to be converted into nitrite. So 0.1 mole over here. We don't have any of that. It's all been consumed. And then 0.18 minus 0.1, and that ends up being 0.08 moles of hydroxide that are left over. The hydroxide contributes in a dominating fashion to the way more to the hydroxide concentration than the nitrite ion does. Yes, the nitrite ion does behave as a base, but it behaves as a very, very weak base, and hydroxide is a much, much, much stronger base. So we're going to ignore the contribution of nitrite to the hydroxide concentration because it's very, very small. Unimportant. Okay, so now we can get the concentration of OH minus by taking the amount of it in moles, 0.08 moles, dividing that by the total volume. The total volume in this case is the 100 milliliters that we had in the beginning plus the 100 milliliters that we had in the beginning, plus the 180 milliliters that we added. That's 280 milliliters, or 0.28 liters. So we end up getting 0.08 divided by 0.28. That ends up being a concentration of 0.29. I'll just do two decimal places here. 29 molar. That's our hydroxide concentration. We're getting close. To get POH, all we need to do is take the negative log of it, negative log of 0.29 molar. And that ends up being, let's see, negative log 29, 0.5. Oh, that 5 is pretty far away. 0.54. That's our POH. And so to get pH, all we need to do is take 14 and subtract 0.54 from it. 14 minus 0.54. And I got a value of 13.46. 13.46 is our pH, right? So let me go ahead for the last time and throw this in the spreadsheet here. 13.46. Okay, so again, this is our finished product, our finished titration curve. So that was many of the calculations required to understand sort of the titration of a weak acid with a strong base. The important thing to remember here is that, well, the equivalence point doesn't necessarily mean neutral pH. That kind of gives a false connotation there, but yeah, you can see at the equivalence point our pH is significantly higher than 7, which would make sense because we have strong base, we have weak acid, so we would expect the base to dominate the acid when the amounts in moles of base and acid are equal. So, yeah, so we can see, like, I don't know if you guys were here last week, anybody who's watching this, I don't know if you were here last week, but the titration curve from last week, what did that look like? That was this right here. So it's a very similar sort of thing. I mean, they're not exactly the same shape, and perhaps it would be interesting if I could plot them on the same graph with like the same, you know, units and axes and stuff like that. I'm not sure how comfortable I am with Excel to do that live. Like I'm sure I could figure out how to add a second data series to the chart, but it would probably be like clunky and it wouldn't really go well with a live stream. So maybe next week or something I can do that and just kind of show you guys both of the titration curves. So again, this is last week's and this is this week's right here. So looks like the this one's kind of flatter, but again, it's hard when they're not plotted on the same scale. So, all right, everyone, that was it. Thank you so much for being here. Thank you so much for watching. Thank you so much for participating. Definitely appreciate it. Next week, I think we might do some like practice problems or something like that. Some acid-based practice or not acid-based, some aqueous ionic equilibrium practice problems. I was thinking about doing nothing but titration problems. Just practice with titration type calculations because I know I go through these things somewhat quickly. So, oh, it's Cam sent me a sticker. Thank you, Cam. Means the world. That's a cool looking sticker, man. Right on. Appreciate it. Thank you for the 99 cents. But yeah. Oh, there's that noise again. I don't know what's going on. Anyway, so let me go back to this screen here. So that was it. Again, thank you guys so much. Yeah, practice problems next week, most likely. So I hope to see you then. All right. Take care.